All right, everyone. So let us continue with our discussion of state space representation. The last time we started talking about certain properties of given state space representations, and we started talking about the controllability property, and we also suggested we will continue with the observability property. So let me mark our video lecture in our series. Okay, so we will have state space representation. This is the fifth video that we are having, and we will start talking about observability. Of a state space representation. If you remember, controllability was related with whether given enough time and suitable inputs, we are actually able to bring the system states from any given state, initial state, to the origin. Okay, so it was related with whether we are able to affect the states by the input. Okay, now observability will be a complementary property, and it's going to be roughly related with whether an initial state is actually visible at the outputs given enough time. Okay, so loosely speaking, okay, again, let me make a loose kind of verbal definition first, and then we will have the formal definition of observability. Okay, so loosely speaking, observability is related with whether the internal states, supposing that they are not visible directly to the outside, whether the states of a representation sometimes people say states of a system, but strictly speaking, this is not correct, because if you remember, for a given system, there might be infinitely many state space representations with each with its own definition of the states. So we are talking about states of a representation. Okay, can be inferred from the observation of the outputs. Okay, so it's like saying watch the outputs and figure out what's going on inside the system. What is going on inside the system? Okay, and let's put it here that given enough time, so eventually, okay, although this eventually, an informal word, can be a long time. Okay, well, it's kind of intuitive to think to imagine that not all system representations can be observable, meaning that by looking at the outputs, you may not be able to observe what's going on inside the system. Let's say if you have a furnace, but you don't have a temperature measurement capability, Okay, by looking at the furnace visually from the outside, you may not be able to say that the internal temperature of the furnace is rising until it's too late and something blows up. Okay. Okay, so let's make a formal definition of observability now. Definition, mathematical definition of observability. Again, the definition starts with the definition for an initial state. We first define whether an initial state is observable or not. So the initial state x0 is said to be observable or unobservable. So the definition is a negative definition. Unobservable if and only if y of t is equal to 0 for all t larger than or equal to 0, corresponding to 0 input, meaning that u of t is equal to 0 for all t larger than or equal to 0, and the system is initially at x is equal to x0. So the system starts from this particular initial state. Okay. So let's also remember our system definition. So we are talking about x dot equals ax plus bu and y is equal to cx, and possibly a du, not always, and this is our system representation star. Okay, a system representation such a system representation is said to be completely observable, if and only if there are no unobservable initial states. Okay, so what we want is that any initial state eventually produces a change at the output when there is no non-zero input, basically. Okay, so let me rephrase that. Any initial state eventually produces an output with no input on the system. Okay, so u of t is equal to 0. Let's also make the theorem that defines how we can actually determine observability. Okay, so theorem, the observability theorem. System representation star is completely observable. That is the pair CA is completely observable. If and only if the rank of a matrix that is called the observability matrix, which is the rank of this matrix generated by augmenting c times a up to c times a to the power n minus 1, is actually the rank is equal to n, or basically the determinant of O is different from 0. Okay, now think about it. Why are we talking about the pair CA, and why is the B matrix not involved here? Well, because in the definition of the observability, the input is equal to 0. The only thing that counts is whether initial states have an effect on the output. And this is related with the matrix A, because states can have effect on each other. And the matrix C, which connects over here, right? Basically the states to the output. So what is important becomes the A matrix and the C matrix on the final outcome. And not surprisingly, O being the observability matrix, and remember that C was the controllability matrix. What did we say for the controllability matrix? I'm not sure. Actually, this is not. This may not be C. I don't remember from our previous lecture. Let me check. Actually, so our controllability matrix was named as Q. Actually, okay. So let's make that correction. Okay, so Q is the controllability matrix. Okay, not to be confused with matrix C, which is the matrix that relates the states with the output. Okay, so this is the theorem which states how we can actually determine whether a representation is observable or not. All right, now if you remember, when we were trying to show that in fact infinitely many state space representations might have the same transfer function, we actually made use of a linear transformation of the state of the type, we defined a new state as a transformation of the existing state, and we actually used a non-singular matrix P, okay, non-singular matrix, which can be inverted. That's why we defined the new state in such a way to make explicitly clear that P is an invertible matrix. Okay. Now I want to state two notes. One is related with this fact. Okay. So the first note, remember that such a transformation in fact did not change the transfer function. So we actually have proven that even if we change the definition of the states, as long as they are related with such a transformation, the transfer function remained the same. Okay. Now we can relate this with observability and controllability. We call such a transformation the similarity transformation. The similarity transformation. In fact, for those of you who will be taking the linear systems theory courses at the graduate level, we'll go into the depth of these definitions. Defining a new state by using new states by a multiplication with a non-singular matrix. Okay, so let's again define this state as p to the power minus 1. Completely, this type of a transformation, in fact, completely preserves the controllability and observability properties of the representation. Okay. In fact, maybe I'm gonna just try to prove this for you in a minute, but let's first, so we say that this kind of a transformation establishes a state space equivalence. Not only that, these two systems have, or the two system representations have exactly the same transfer function. If one is completely observable, the other is as well, and if one is completely controllable, the other is as well. Let me also state the second property, which relates with what happens when you are deriving the transfer function. So if there is a pole zero cancellation in the transfer function, derived from the state space representation, the representation will be uncontrollable, unobservable, or both. That means it cannot be at the same time both controllable and observable. Okay, remember that we can put the state space representation into its observable canonical form, and I'm going to show you an example in a minute. Okay, if we put it into observable canonical form, it's going to be observable, but it will not be controllable, and vice versa. Okay. Okay, so let's take a look at an example that actually substantiates the second note. Okay, example. So let's say that we are given a transfer function in which we know that there is a pole zero cancellation. I will not perform the cancellation, but we know that there is one because s plus 1 is one of the factors of the denominator. So if we wanted to cancel those pole and a zero, in fact the system would have been reduced to a further, actually a first order system. Okay, so in this TF, there is a cancellation of a pole and a zero. Okay, so but still we want to put this, we want to treat this system as a second order system, and we want to obtain a second order state space representation. Okay, let us consider it as a second order system, and check observability and controllability. So in fact, what we are saying here is that in fact we have a second order system which has two internal states, but if we derive what happens from its input to its output, it actually behaves as if it's a much simpler system. Okay, so the translation from the input to the output does not reflect entirely what's happening inside the system. Okay, this is actually, this might be quite common. Okay, so let us put this system into its controllable canonical form. So we can do this directly from the coefficients of the system, right? We will have 0 and 1 in the first row, and then -1 and -2 in the second row from the coefficients in the denominator polynomial. We have b is equal to 0 and 1, and c is given from the numerator polynomial, and we will have 1 and 1. Okay, now we know, and we have proven that we know that this representation is completely controllable because it's in the controllable canonical form. Controllable. But what about observability? Let us check observability. In order to do that, we will simply construct the observability matrix. O is equal to C and CA. So C is given by 1 and 1. C and A becomes -1 and -1, another row matrix. Okay, so if you take a look at O, there is actually linear dependence between the rows. Okay, the second row is actually a constant times the first row. So if I calculate the determinant of O, it's going to turn out to be 0, right? 1 times -1, -1, minus -1 times 1. Okay, so that is equal to 0. Okay, not completely observable. Now we can do the counterpart. Okay, we can do the same. We can put the system into its observable canonical form. Into observable canonical form. Again, directly from the coefficients. So I'm going to have 0 and 1 in the first column. I will have -1 and -2 in the second column. BO will be equal to 1 and 1. And CO will be equal to 0 and 1. Now we know again that this is necessarily completely observable. But this time we need to check controllability. Check controllability. Okay, so in order to do that, we construct the controllability matrix. This is given by B, AB. We know that B is given by 1 and 1. AB given by -1 and -1. Okay, so again, determinant of Q is equal to 0. So it is singular. It is not full rank. Okay, and therefore not completely controllable. Okay, so that is what the second property tells us. Let me also consider a side note. In fact, this is something that we will not make explicit use of in the context of our of this course, at least. Okay, so it is again related with this similarity transformation based on the first note above. Given a system representation, x dot equals ax plus bu, y is equal to cx, okay, which is completely controllable, meaning that we have determinant of q non-zero, therefore q is invertible. Then there exists a suitable transformation of the state given by a P matrix that is invertible. Then there exists a suitable transformation such that this transformation puts the representation into its controllable canonical form. Okay, so what is that representation? X dot is equal to in fact, in this case, we should put it into in terms of the new state, phi dot is equal to P minus 1 times phi plus P times B times U, and y is equal to Cp minus 1 times phi. Okay, and this will be in controllable canonical form. Okay, now in fact this can be proven by finding the new controllability matrix. Guys, I think I have made a mistake here, so let me correct. This is not P minus 1, but it has to be P to the power minus 1 AP, P to the minus 1 times B, and instead of Cp to the power minus 1, it has to be Cp. Okay, so let me correct that. And in fact, we can actually check that. Okay, so let me erase this part. Okay, let's make that calculation to convince ourselves that this is the case. Okay, so remember we have phi is equal to p to the power minus 1 times x as our new state. So remember what we have. We have x dot equals ax plus bu. Okay, so we have basically, let me try to write down what phi dot is. Phi dot is equal to p to the minus 1 times x dot from here. And that is equal to p to the power minus 1 times x dot is equal to ax plus bu. So that becomes p to the power minus 1 ax plus p to the power minus 1 times bu. But also from here we know that x is equal to, because p is invertible, okay, we can re-invert p to the power minus 1. So I'm going to have p's x is equal to p times phi. Okay, so if I replace it here, so I'm going to have p to the power minus 1 a, and x is equal to p phi. So I will have p5. So here's your new a tilde matrix or a bar matrix, whatever, plus p to the power minus 1 b times u. And this is your b bar matrix, your new b matrix. Okay, so this is phi dot. So that is your new state equation. And what about y is equal to c times x? Now it is clearly equal to c times p times x. Okay, sorry, c times p times phi. Okay, so that is our new C matrix. We can call this C bar. Okay, so that actually verifies that we have these three new matrices. Now let us continue with our discussion. The new controllability matrix. Okay, the new controllability matrix will be equal to, let's call this Q bar. Q bar will be equal to B bar A times B, A bar B bar, up to A bar to the power n minus 1 B bar. Okay, so that's going to be the new controllability matrix. Now if I expand this, and I know what B bar is. B bar is equal to P to the power minus 1 times B. A bar is equal to P to the power minus 1 AP. And B bar is equal to P to the power minus 1 B. Okay, so this is my A bar, right? Now what happens here is that this p to the power minus 1 becomes the identity matrix, and for the last part you have a bar to the power n minus 1. So you will have n to the power minus 1 times p minus 1 a p, p minus 1 a p, etc. So a bar etc. So what you will have is that in every one of them there will be a lot of identity matrix, and you can see that a's remain here. Okay, so this whole thing will be equal to p to the power minus 1 a to the power n minus 1 times in the end you will have p to the power minus 1 b. So p to the power minus 1 is going to be combined with p to get you an identity matrix, and finally you will have a b here. Okay, so what this tells me is that you see you have p to the power minus 1 terms in the beginning. So you will have p to the power minus 1, but inside you will have b, then ab, and finally a to the power n minus 1 times b. And this is nothing but the controllability matrix of the original system. Okay, so that means that the controllability matrix of the new system is actually equal to p to the power minus 1 times the controllability matrix of the converted representation. Okay, so in fact we're not going to go into too much details, but this may be used to find P. Okay, this suitable transformation to put the system, the representation, into its canonical form. Okay, later. Okay, so in fact at some point in your control lectures you will see how you can put the system into its canonical form directly, and the way to do that is that you're given a state space representation. You first find its transfer function, then use the transfer function to put it into its canonical representation. So if Q is computed from the given representation and Q bar is computed from its canonical form, from these two matrices you can actually extract P, which is the transformation that puts the system into its canonical form. Okay, so this whole part is like an interesting side note, but I would say that this is not included in, at least in EE302. Okay. Okay, so let me take a look at my notes. All right, so this looks like it's a good point to break. Okay, up next we will start talking about how we can use these concepts, in fact, in order to design controllers for state space representations. So our topic will be pole placement by state feedback. Okay, basically we will discuss this as a way to design closed loop systems, a powerful way to design closed loop systems where closed loop poles can be arbitrarily located. Okay, so we will have a extensive discussion on how to do that. Okay, so that is where we stop for today.